In this video, we're going to discuss continuity and piecewise defined functions. Here's a graph of a piecewise defined function that is composed of three different line segments on different parts of the domain. If I were to sketch this graph, I see that I never lift my pencil, and so in our intuitive sense of continuity, this function is continuous everywhere. So we do know that there can exist piecewise defined functions that are continuous everywhere, or I should say everywhere on their domain. I could also sketch this graph. So maybe it looks like this, and then up here it looks like this. So I have two different functions, this is my piecewise defined function, and it's defined this way on this piece of its domain, and it's defined this way on this piece of its domain. And we can see graphically that this is not continuous because in order for me to get to here, I have to lift my pencil. So this is an example of a piecewise defined function that is not continuous everywhere, and in particular it's not continuous at this a value. But it does look like it's continuous everywhere else. Let's look at a formula for a piecewise defined function and see if we can see which problems or what kind of problems can arise. So if I were to look at this, so it's defined as x squared for x less than 3 and x plus 3 for x greater than or equal to 3. And so here I might make the mistake of saying, well, x squared and x plus 3 are both polynomials, so they are both continuous, and that would be correct, but the problem is what happens at the place where they change definitions. Because in this example right here, this was a line which is continuous everywhere on its domain. This is a line that's continuous everywhere on its domain, yet they had a problem at the place where they changed definitions. They split apart, or they aren't connected graphically. So in this case, when we know that each piece is continuous, we still need to look at the place where they switch definitions, and that happens at 3. Well, before we do this formally, let's see if we can sketch the graph and answer the question graphically. So it looks like the parabola x squared for everywhere up to x being 3. And so if it were defined at 3, it would be 9. Say that's 9 right up there. Okay, when x is 3, it becomes this line. So it is 6 there. And it is a positive slope going that way. So here, even though it's continuous everywhere for values less than 3, and it's continuous for every value greater than 3, at 3, we have this disconnected graph. So here my function is not continuous at x equals 3. Okay? All right, let's look at another example. Let's look at this function. F of x equals x squared, and this might look familiar, minus 3x minus 10 all over x squared minus 8x plus 15, as long as x is not 5, and it's equal to 7/2 when x is 5. Okay? Now before, when I asked you this question, we were just looking at this function, and we discovered, or we recognized that this was a rational function, which meant it was continuous everywhere on its domain, which upon factoring, let's rewrite it in our factored form, we have x minus 5x plus 2 over x minus 5x minus 3 when x is not 5, and 7/2 when x is 5. So if it were this function alone, we would say this function is not continuous at 5 and 3 because it is not defined at 5 and 3. However, this function, which looks like this rational function everywhere except at 5, but I do assign it a value of 7/2 when x is 5. So I know that my function is not defined at 3. This tells me this, and I don't make up for it anywhere else. So I know that this is a place of discontinuity because the function doesn't exist there. Remember, that was my first condition. F of 3 does not exist. Right? We have an issue here, and I don't make up for somewhere else. But the question is, what happens at 5? We can't say it's not continuous there because the function doesn't exist there, because it does. It's 7/2. So what we now need to check, remember, because there were 3 conditions, we need to see if the limit as x approaches 5 of f of x equals f of 5. That's the question. And if this answer is yes, then we conclude the function is continuous at 5. If this answer is no, then we conclude that the function is not continuous at 5. So let's see. What is the limit of this function as x goes to 5? Well, how is my function defined near 5 but not at 5? Well, it's defined this way everywhere that's not 5. So that means near 5 too. So x minus 5x plus 2 over x minus 5, x minus 3. Now I can cancel these. This limit is equal to this limit because this function is equal to this function everywhere away from 5. And so since I'm not at 5, I'm near 5, these are equivalent. Now, I can do direct substitution provided I don't get 0 over 0. So if I plug in 5, well actually if I don't get 0 on the denominator, if I plug in 5 I get 7 over 2. And by the way, that is in fact what f of 5 equals. So I have shown that the limit as x approaches 5 of f of x is indeed f of 5. Therefore, f is continuous at x equals 5. Go do some practice.